seminar in the spring semester, and we're happy to have Boris Tsygan from Northwestern, who will speak about the Gauss-Manin connection in noncommutative geometry. Boris, please.
Okay, thank you very much. So let me start with the classical case. If you have, let me have, for starters, let me have a super scheme, specter of a Z2 graded or maybe Z graded commutative algebra. And so the functions are themselves a graded algebra, Z2 graded, and this is, it also has Z grading, and it has a differential of degree 1 and square 0, the forms. Now, this is a natural construction, so if you have a vector field, which is by definition, let's have an odd vector field, k-linear, or maybe there will be a nuance, and so it's not homological, it won't be flat or square, or it won't be 0. But on forms, it can be flattened, and let me do it in a little bit of a slightly unusual version. Let me introduce a formal parameter of degree 2, which is u. I think of degree -2 if it's homological degree. And then its flattening is of total an operator of total degree -1 on forms. And it's u times d plus your vector field plus this extra term, which is contraction. Yeah, by the way, lambda square is also a vector field, correct? It's also a derivation when lambda is odd, because commutator of derivations is a derivation. And if you correct it like this, it becomes flat. So this is the flattening or the Gauss-Manin version of lambda. Now, how canonical in this is this procedure, and in what sense? Well, formally, it's kind of canonical. It's independent of lambda. Namely, if you have two...
Boris, sorry,
yeah.
your D is what? Your algebra doesn't have, it's just the Rham differential, what?
D is the Rham differential, yeah.
Yeah, all right.
And lambda is an odd derivation of the functions, therefore of forms as well, and you can flatten it adding this term. Now, if you have two odd derivations, you have two operators of square 0, and formally they are conjugate. What does it mean? Formally, the isomorphism between the two is this one. So it's a little bit, you have to have some kind of smallness condition of lambda 0 minus lambda 1. Great if it can be nilpotent, you know, but maybe even more. Or you can say that it is independent on lambda in some completion that you have to specify. And then if you have three lambdas, then you have this condition. So basically it tells you that it's lambda, this Gauss-Manin construction is as canonical as it can be, you know, it's the two are isomorphic, and the three, if you compare, it's a coherent isomorphism. Okay. Yeah, now Gauss-Manin, there is a, yeah, sorry, maybe there is a bit of, should I, yeah, you are right, should I call it dr and not d, and then maybe K is a differential graded algebra itself, and then the derivation should be not K-linear, but it should be compatible with this derivation. You know, lambda of, I don't know, k times a is gk times a plus minus a times k times lambda of a. So you could repeat the same flattening construction, and then you apply the previous thing when your, well, differential graded algebra K, algebra of scalars, oh, I'm sorry, not algebra of scalars, functions on your graded manifold is forms on the base times functions on the total. So it's function valued forms on the base, and forms on your scheme is this. And if you have what is called an Rham connection, which is, you know, the connection in this, well, infinite dimensional vector bundle. Again, it may not be flat, but it can be flattened by the same procedure. And this is the Gauss-Manin connection that you obtained precisely from the by that construction from the previous page.
So this Rham story, I mean, if I have indeed something locally trivial, then I do have whatever you wrote. So you call,
yes.
Okay.
Locally trivial, yes, but actually, if everything is smooth, if it's a smooth morphism of smooth schemes, then the Rham connection exists, I won't say micro-locally, it exists locally in the base. I'm sorry, it exists locally in the total space.
Yeah, but to have it kind of locally on the base, you need some properness condition or what?
Well, local triviality, properness, I'm not sure.
Yeah, okay,
Yeah,
good. Local triviality will do.
Yeah.
Okay, I agree.
But locally on the total space you can do, and then you get, I mean, your complex with this flat connection, it's actually an operator on of square zero on the check complex. Okay, yeah, of course, yeah, so I'm following here, first of all, Manin, as understood by Grothendieck Katsoda, and this Gauss, again, locally in X, this Gauss-Manin complex is, it has a canonical meaning, it's just the total de Rham complex of the total space, but it can be understood like that, like forms on the base with respect of a family of complexes on the fibers, I would say, and the differential of square zero. Okay, so this is the classical case. And of course, well, as understood by Grothendieck, probably it actually uses some calculus, Cartan calculus on forms, which exists in commutative geometry. And
what does it mean, can specialize at U equal 1?
I mean, this formula, I mean, maybe let me see. So this formula, we define it, so it would be
this
better.
formula, okay.
And these two, if you have two connections, then their difference is nilpotent. So it's actually a finite sum.
Is it nilpotent?
Yeah, because their difference is of one form.
On the line, yeah, okay.
Yeah, on the base, yeah.
But but if degree of U is -2, what does it mean that U equals 1?
No, yeah. Yeah, this you can do, but you can parallelly say that it's a degree 0, and there is an extra grading somewhere. I mean, well, in this case, I mean, there are two gradings in this case, one with respect to the base and one with respect to the fiber, and then they agree with each other.
So this means that when you say u equal 1, you simply shift the grading, you still shift the grading of whatever of differential forms by -2, but you do not. So it's really kind of a bookkeeping of the grading, the role of variable u.
Yes, I mean, you have G, what I call G, the Rham is GS, and the Erisman connection is and delta square will be what? It will belong to vector of this, which is, I would say, derivations of degree. I mean, well, iota delta square is an element of omega 2. Something like that. Yeah. So the degrees all agree, but for non-commutative geometry, we will see that we are actually in this case, or we better work.
With a variable u. Okay.
It's kind of it will become kind of confusing and also intriguing, because in those formulas, this u is very much like the Planck constant. So that's another I don't know, food for thought. Let's try to see, maybe.
All right, thank you.
Yeah, thanks. Okay, now non-commutative sort of forms. Instead of a super scheme, you have, let's say, a graded or Z2 graded commutative, associative algebra.
But K is still commutative?
K is still commutative, yes.
Okay.
And instead of this, you have the periodic cyclic complex. I will say more about it. It's over K, so maybe I should say, over the scalars. So I will define them a little bit later on another slide. So let me recall that there is the Hochschild complex, and you multiply it by power series in this formal variable. And this is the differential. So unlike the forms, there was no differential on the forms. So like you see here, without this u, this was the graded space. And this is already a complex of homological algebraic measure, the Hochschild complex. And so that what replaces the forms. Then again, you can have an odd differential form, odd derivation. And you can, well, the fact is that, again, formally, and I will explain why formally, you can flatten it. You can flatten it, so what will it be? It will be some well, operator, well, in the formal completion of the periodic cyclic complex, so we will see that unfortunately it will be actually it will be strictly negative degrees for some reason. So one has to be careful. Like we already saw that with the exponentials, one has to be careful whether such a thing exists. And again, an intuition is that when lambda square is not zero, so we have to flatten it, but when lambda square is small, then you can flatten it as an operator on the periodic cyclic complex. So the claim is that yes, you can flatten it, and so actually there you can define an formally as an infinite series Antieu inverse. You can define an operator in whose argument is an even derivation. It will involve infinitely many terms, so great if it is nilpotent. If not, there is an issue. It's not linear in the argument R. In fact, it will be a formal series of homogeneous equations in R, linear quadratic cubic. And again, in the same formal sense, if you allow infinite series Antieu inverse, then it's kind of canonical. Namely, for any two odd derivations, you have an even operator like this. And then if you, the coherence, this etc. means that if you multiply t lambda 0, lambda 1, t lambda 1, lambda 2, it's not equal to t lambda 0, lambda 2, but it's equal up to homotopy. So there will be some homotopy t of 0, lambda 1, lambda 2, and then there will be higher homotopies, and they all are packaged into something.
So this existence of T capital is not as obvious as in the commutative case. It's not given by a simple formula.
No.
Yeah.
It's given by an intriguing formula, I would say. Yeah, not simple.
So simple can be intriguing, but go on.
Yeah, not so simple, but so it will start with the exponential, and then it will kind of what I call higher exponential, which to me reminds me a lot of some mathematical physics. So maybe you could, see something. Yeah, and again, maybe let's not dwell on it, but again, if you have an algebra over OS and our graded algebra is algebra valued forms, then you get Getzler's Gauss-Manin connection. Superconnection at the level of complexes. There is one nuance that this Ehresmann connection, the Ehresmann connection there was supposed to be, a connection with values in vector fields, so to speak. So it should, in this case, it should be a product preserving connection. It should be a connection with values in derivations of the ring. And those, there is no such notion as locally in A or in the total space. So it's hard to say what it means. But there is another trick that if there is no such a thing, you can pass to a bigger model, to a bigger complex. So in some sense, it's a little bit like you are passing to the Czech complex on the total space, but it's different. I think I will be able to say something about it later. Okay, but for now, maybe let us just concentrate on what on this flattening procedure and what it entails. So, what's the goal of the talk? The goal of the talk, first of all, well, to give some precise statements. So again, for every odd derivation, lambda, or you could say for every even derivation, lambda square, in terms of lambda square, and for every two odd derivations, etc., I promise that I will construct some operators on the periodic cyclic complex with some algebraic properties. So for me, maybe the main goal is, so one goal, why are those operators there? How to deduce them from some sort of first principles? And by the way, how to deduce, so to speak, the non-commutative de Rham differential capital B from those first principles? So what kind of non-commutative differential calculus is there, and why it is there? When and in what sense do those operators converge? And there are, it could be, in p-adic topology, part of what I am saying, part of this could be defined over Z, could and should be defined over Z. And then I hope to show you that it leads to, well, non-commutative crystalline cohomology. It leads to some operators on suitable completions of the periodic cyclic complex. Should we look for, and why, if we want them to converge? Okay, and finally, the formulas for them, they are just dripping with allusions to, well, to the beginnings of calculus, but and then to more advanced calculus of the modules, and also to mathematical physics. And again, kind of very intriguingly, this, as you are right to say, this formal letter of degree 2 exhibits a lot of similarities to the Planck constant.
So basically, it's not about Gauss-Manin connection. There will be more operations, and Gauss-Manin is just a byproduct of this bigger package.
I would say so, yeah, but probably, yeah.
Okay.
But I mean, the Gauss-Manin package, when I say this, and then I say this, and then I say...
You said it's Getzler, and Getzler can contain a lot of other...
No, I mean, this is also, I would say, a part of the Gauss-Manin package. You know that if you compare two Gauss-Manin connections, they are gauge equivalent. If you compare the three, now you have two comparisons between the first and the third. And those two are homotopic, and this is the homotopy. So this is also... But there will be more operations, that's correct, yeah. Okay, so as you see already here, you see some flavor, like, those fast oscillating exponentials, especially if it's, maybe I should say that rather it is, IH and not H. Okay, yeah, Cartan calculus. So again, in the classical situation, if you have a vector field, let's say even, but again, even or odd, let's say even. You will have an even operator on forms, of course, but also you have a Lie derivative, but also you have an odd operator on forms. And they satisfy those two equations, which, if you combine them, you will have one equation. And again, it's a bit awkward because in the classical kind of notation, of course, they are separately equal to zero. They have different degrees.
But in the right-hand side, you have d or Lie derivative of d in the combined formula.
It's the same. Yeah, I'm kind of.
Okay.
Yeah,
Slightly abuse.
Yeah,
okay.
yeah. Because I will be kind of making, I will be confusing them if I fix notation, but I mean, yeah, both are good. Okay, but on the other hand, so if I add this formal variable here, then I get to, yeah, here it is. It's two expressions of degree -2, and they are equal. Okay, in non-commutative differential calculus, what should we expect? So first of all, again, this I will recall what they are. So let me just say that this is the periodic cyclic complex. It's the localization at U of the negative cyclic complex, and it has two differentials, one Hochschild and one cyclic. And of course, derivations act on it. And so what do we expect? There would be, and again, the analog of iota d.
So Cn is negative here.
Yeah, Cn is negative. Yes.
Okay.
Yes. Cn is negative. You will see in a second why. I expect for any even derivation, I expect such an operator, correct, no denominators, satisfying this formula. And why do I need to invert? Because like I did in the commutative case, this is where my denominator comes. Yeah, but J of D doesn't involve denominator in U. So this is what I expect. And yes, I will have it, again, a bit formally, because, no, I'm sorry. No, this exists not, let me think. No, yeah, this is some formal expression, some infinite series in D, not in U, but in D. Okay, yes, it exists. We will but this is not the basic thing that exists. What is the basic thing? And here I denote it by I and give it kind of greenish color to distinguish. And the relation for the differential is this. And you see it's a different relation, which I think immediately brings to mind, I don't know, taught class and multiplicative versus additive and this sort of problems. Again, now I claim that it exists. It's a formal expression. What actually exists? What exists is its coefficients. So if I write
well, what's the meaning of the right-hand side? You have some.
It's an operator on the, an operator on the power series in U. So one again, maybe let me. Yeah, so I am working in okay, and again, I will write it later, but for those of you. This is the definition, well, not of the differential, but of chains. Differential, I hope to review quickly later. So it's so on the one hand, you have this and exponential of UG is a perfectly well-defined operator. Correct. I have power.
Yeah. I mean kind of geometric meaning. So it's exponent. It's kind of like automorphism.
Yes. I'm coming to it. Yeah, correct.
Okay.
Yeah. And I claim that, yeah, and again, so as you see here, you better assume that Q is in K. A lot of it will be defined without denominators, but so this is perfectly well defined. So I claim that there are other operators again, perfectly well defined. And it's a little bit suggestive and confusing people. So all I am saying is well, of course, you know, D is an operator from A to A. So D is like a differential operator on A to A. So you would ask that, or people ask, maybe you don't, but unfortunately people ask, whether this is a function of this. No, not really. It's in some sense, yes, hence the notation, but not really. It's just some homogeneous expression of degree n in D with values in operators on complex. Okay, so those exist, and by the way, they are defined over Z, no Q needed. And if you formally write, I'm sorry. It's not a formal, I mean, it has infinitely many terms, you know, but it's kind of a generating function and it involves denominator, but this one satisfies the formula it satisfies this formula that that allows me to, well, that allows me to proceed. Right? That exists, you know.
Okay.
Any questions?
No, I'm fine, yeah.
Okay. Yeah, and so for every individual finite level n, these are perfectly well, you know, satisfied formulas.
Yeah, sorry. So I wanted to ask a question. So do you require D or maybe I sub Dn? So maybe D to be locally nilpotent or something, so that for every argument I sub Dn equals 0 for all but finitely many n's, something like that.
For those formulas, not at all.
So they're just formal sums.
No.
There is a
No,
formal value
here,
for
no,
U here.
this is for individual n, yes.
This is an actual finite sum. Everything here is a finite monomial. I mean,
Yeah, and for the previous formula with I sub
for
D.
the previous, it's so far it's a formal expression. I mean,
Okay.
for it to make sense, you need you need, yeah, either it makes sense in some completion or.
I guess you probably have some kind of divided power structure requirement on this side.
Yes, correct. Yes, so maybe should I say that what will happen is that oh yeah, good question. So when this is p-adically small, then well, what I will use is something like this, and I will use some variation of that. Yes, it's a perfectly well-defined operator on. It will be a well-defined operator on the p-adic completion of the periodic cyclic complex. Yeah, for example, because correct. Well, when p greater than 2. Yes, that's okay. So, unfortunately, when I say this, whatever, what I called it, etc., or something, it's because I would need not this green expression, but this relation, but this yellow relation. And that's not what comes naturally, but one can be expressed through the other. And maybe before doing that, let me real quick say why the green and not the yellow, and also why the capital B. So maybe finally, let me define my Hochschild chains. Here is the definition, and crucially, they have another argument, which is a bimodule over A, and there is a Hochschild differential. Here it is for completeness. And again, this underlined first or zero argument is actually in the bimodule. Okay, and in particular, as Jan said, let this be an algebra endomorphism, then it defines a bimodule by this formula. Of course, well, we know that actual, probably more correct version of morphisms of algebras are bimodules, but let us consider those special bimodules. And then you have two operators on this complex which commute with everything, and one is identity, and the other is just applying this endomorphism F. F commutes with itself, and the formula is that just multiply, I mean, apply f to everything. And then there is this kind of, I don't know, proclamation that they must be homotopic. Those two must be homotopic. How can one see that? One explanation is that if you realize that it's the derived tensor product, it's kind of automatic, and maybe at the zero level, so you act on a zero chain, yeah? A minus f of a, yes, it is a differential. It's a differential of one tensor A. And I mean, when you understand what this kind of fat L or bold L is, they must be homotopic. And yes, there is an explicit homotopy. So you have this formula. And when you specify it to f equal to identity, you get this. So I kind of like it because I don't know. B is noncommutative the Rham differential, and so I sort of like it that it's like I am differentiating, yeah, like I am shifting the coordinates and then evaluating this, making the shift close to 1. So okay, the other explanation, one could argue that this structure should be tight. What does it mean, tight? Maybe so what always comes to my mind, I am sorry, I don't have time to elaborate, but for those who know, what always comes to my mind is this joke, probably from the Soviet 60s, where they talk to Stalin and the punchline is "Зачем вам два Синявских?" So for those who know, they know, but they don't have time to elaborate on that. So there shouldn't be any natural morphisms dangling around. There should be a tight structure. And by the same argument, you realize that the square should be 0, because again, the square of capital B is not 0, but it's a natural transformation dangling around, so it should be homotopic to something, etc., etc. And maybe the one thing I would say that what kind of the tight structure, maybe let me give you one. One way of saying it. One way to say that it's a tight structure, that rings, as we know, to form a 2 category. And if you do it at some derived, higher or p-adic level, is basically the Deligne conjecture in some sense, and or Ekman-Hilton principle, I don't know. And if you include chains, it's not just a 2 category, it's a 2 category with a trace functor up to all higher homotopies. And however you formulate it, you get those conditions. Okay, and if you formally apply those operators to exponential of the derivation, as Jan said, and just define it like this. This is your definition of I of D and all of its homogeneous components. And by the way, the explicit formula for when you are looking for the homotopy, everything is good, but crucially I forgot. Yeah, as you saw in the formulas, I forgot to multiply it by 1. If you look at the formula, then you will recover that they are absolutely explicit. Okay, so intriguing formula number 1. So we are, as I said, to do the Gauss-Manin argument or construction, I need this yellow system of operators and not, R is same as D, an even derivation. Now, I have constructed and explained those, how to pass from those to those. And this is, here is the first intriguing for me thing. The explicit construction is this. First of all, you now have 2 sorts of operators. You have those IDs that I have constructed, but also I have the Lie derivative and its powers. So for every monomial in 2 variables, I can construct this operator again. It's a perfectly well-defined operator on the negative cyclic complex array for every even derivation. Very good. Now, to construct my J, and let me involve this U like I do in Gauss-Manin, because again, it's kind of intriguing, I would say. So, well, it will be a sum. It will be something corresponding to a sum of monomials. So some function in W and Y, and also U dependent. What function? Here is the function. Here is the function. And it's by Newton binomial, you can write it like this. Whereas I of D over U, the thing that it corresponds to this function. So instead of this, you have this. And as we know from the very beginning of calculus, it's what one of the, maybe the first, I forgot, of those fundamental limits. When W goes to 0, at the level of power series, you see it immediately, but it also, I think, what differential and integral calculus starts with, at least how we were taught it in the Soviet Union. Okay, so let me mention Geo briefly, and again, I find it kind of intriguing that these same formulas appear in some sort of Laplace transform for D modules. If you have a function on a manifold or variety, then you can form a formal D module like that in the left-hand side, which also has D module meaning in terms of direct image of you have this. And also you have a different kind of D module where you multiply by this formal thing, and S acts via minus HD over DH. And then you have a morphism from one to another, which is given by that formula. And it does intertwine S with this, So, of course, it's some sort of formal Laplace transform.
So this f corresponds to your f previously? I mean, no.
I don't think I had an. I mean, here I have f here and
No,
f
no,
here.
I do
Yeah.
not mean just notationally, I mean kind of
Mhm.
really. Because
I mean, in the presence of a function, I can construct 2D modules. This is one, and this is another. And this is a morphism of the modules between the two. Same f, yeah. And it's some sort of formal Laplace transform. And also, we are talking Hochschild and cyclic homology, and some, anomalies between them and the commutative calculus via HKR. And in the filtered circle of Moulinos, Robalotto, and Raksit, Achille, Matthew, same formulas appear, and as some morphisms of formal groups. And so there must be connection, but I don't know. Yeah, so let me skip this. So both relations did appear in the literature, as pointed out to me by Anton Alexeyev, and also one can make a statement if you have a DG, let's say, Lie algebra, then you can form two DG algebras out of it, so one yellow and one green, and let's say if it's a one-dimensional even Lie algebra generated by, so should I say maybe, in case of a one-dimensional algebra, we recover the previous algebras acting. And so one can define them with generators and relations. Maybe let me skip that. And so you have the yellow A0 and the green A1. And the theorem is that A1 of, A1 of der of A naturally acts on the negative cyclic complex of an algebra. And A1 of how about A1 of the big algebra of replacing derivations of the big algebra of Hochschild cochains? It also acts on the negative cyclic complex, but on its bigger version. And again, there is an explanation, but maybe let me skip it because I wanted, so there are sorts of convergence questions. Maybe let me skip that as well. But again, at least for me, it seems like plausible that because of those formulas before, there is some chance for those formulas to be convergent in the Archimedean sense, but the presence of this Laplace transform maybe suggests that some resurgent methods in this kind of Planck constant U may be in order. Yeah, and finally, intriguing formulas too. So I would like at least to mention that those are those things, lambda gn and t lambda 0, lambda 1, they are given by formulas. And we have seen when we look at explicit formulas, then again, I would be very grateful if somebody could. So first of all, as before, I was able to encode some operators in the negative cyclic complex by monomials in two variables. Monomials in two variables. Yeah. So if I am looking just at this, or rather, no, never mind. Yeah. But those were very special operators. Now I have a non-commutative algebra, and I can write monomials that won't commute, and I can encode them by monomials in commuting, but more than two variables. So correct, if I have just never mind the ... I can encode this element in a product of four monomials as an honest polynomial in four variables. And as mentioned, I think by Maxime, as mentioned, it looks a lot like Ekal, by the way, by itself, what Ekal did. And again, maybe it's not the place to dwell on that, but just let me say that the operators that I am going to describe, they will be encoded in some natural way, but doesn't even precisely matter in what way, by polynomials in infinitely many variables, happen to be in infinitely many x's and infinitely many y's, like this. Infinite sums of them. What kind of infinite sums?
Sorry, Boris,
So,
X and Y commute? Okay.
Yeah. X and Y commute is just, again, a bookkeeping device. I have some way of writing a product of non-commuting monomials as to encode it as a polynomial in infinitely many commuting variables. And I mean, it shows how I do it, but maybe right now, never mind. Maybe just let me say that there is a natural way, and those operators that I am going to describe, namely, for example, this operator. So in the classical, in the previous life, it was an exponential. So maybe let me just say that it was encoded by a function in one variable, something like and the formula for this transition function, t of 0 lambda, will be something encoded by a function in infinitely many variables. And again, probably let me just indicate, like hopefully in a minute, what kind of infinitely many variables, what kind of function of infinitely many variables. So it lives in completed space of full polynomials of infinitely many variables. So in sort of a Fock space. So I want to act on the usual exponential in one variable and obtain something more involved from it. And I will be acting by the following. So first of all, there are creation operators. Then there are annihilation operators. So I will be acting on the exponential of x0 over u by some creation operators, actual exponentials of those, annihilation operators. But then there is the third class of operators that I don't know, I haven't seen in physics, and I asked a couple of people and they also haven't seen it. And let me finish with that. It's some sort of annihilation / creation operator. It's kind of finite derivative, so, or difference operator. It takes a function in one variable and produces a function in two variables, correct? Out of xj, you get a function in xj plus 1, xj plus 2. So if you have infinitely many variables, then correct, I mean, this is a formula for my operator. I call it, I don't know, creation / annihilation. I know, maybe there is some vague resemblance to vertex operators, I don't know. And then there is an explicit formula like that for the operators. And so I don't know, again, for me, it's just dripping with some sort of physical allusions, but I don't know. And again, U plays the role of IH. Yeah, so maybe let me finish here. And well, in the notes, there is also an explanation how to define non-commutative crystalline cohomology for an algebra over Fp. I haven't come to that, but here it is. Okay, sorry, thank you very much.
Thank you. Thank you, Boris, for intriguing talk with intriguing formulas. So, questions?
Can you say a little bit more about the just very briefly, but the crystalline cohomology in the non-commutative setting over a field of Fp?
Yes, so
The
really,
rough, you have the divided power structure somewhere, and you have the A to be still a dg.
Yes. So, I mean, real quick, if you have an algebra over AP, should I say ZP?
And you probably can take the.
I lift it. Yes.
I see.
And well, I lift the product some.
Lift to the ring of with rings.
No, I would say that I somehow or rather, I'm sorry, M is in G1 and M square is in G2. And so it's a Hochschild cochain. And I said that Hochschild cochains, they're not derivations, but you can do it. They are co-derivations of the bar construction. So you could pass so there is this version, and if you want, it's this is what I explicitly mean. And so everything, you know, M square I or J of M to N, blah, 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 they all act on this complex. And you can, I mean, M Gauss-Manin, on the because of this condition, on the p-adic completion is well defined. And independent on the lifting because of those. You could. So this is a well-defined kind of crystalline non-commutative.
I see. So you're not doing things to how the in the commutative case the divided power structure.
Yeah, I should. Yeah, maybe it's a good point. Yeah, how to explicitly compare it. Yeah, that's a good point.
Mm-hmm.
Yeah, I am not sure. Yeah.
Okay. Yeah, thank you.
No problem. Yeah.
More questions?
Yeah, I'm sorry, I have a fairly technical question. So, yeah, I wanted to ask about the explicit formula for capital B sub f.
Okay.
So what is the summation? So do sum over all integers or do sum from 1 to n?
I mean, you sum over all the cyclic permutations. So J equal to 0 to n, I guess. Yeah, there are n plus 1 cyclic permutations.
So that's what you do when f is identity. So for
No,
non-identity f, you do the same thing, right?
I do absolutely the same thing.
Same
The
thing.
only difference is that
Right. Yeah.
up to
Yeah. Yeah. Thank you. Yeah. The thing is that we've came across a very similar operator, but in our case, f f has finite order, and we would really like it to be over all like n times the order of f possible permutations with applications of f. But yeah, I don't know if that makes sense. Thank you.
Yeah, no problem.
F some kind of defined shifted diagonal in the non-commutative sense.
Yes.
More questions? But I have a question, kind of the old stuff, but I would like to put it in the context. So you know this calculus which we defined with Maxim like 20 years ago. So the action of some, let's say, operad of chains on the cylinder with marked points. Yeah, okay, so you know this very well. So in what kind of, you know that it's quite recently this guy, heard it him in Miami, Zhihong Chen. He wrote a paper where he compared the operations which come from the action of this operad of chains with a Gauss-Manin connection, and basically one of his results that is it commutes Gauss-Manin connection commutes with all operations which come from our operad with Maxim, operad of chains on the points on the cylinder with some points inside and some on the boundary. Yeah. So then, which means for individual Gauss-Manin connection, the whole structure which comes from the action of operad and just translated along the, if you like, along the moduli space, it is preserved. but you build some operations for collections of Gauss-Manin connections, so how to put that story, how to combine them?
I mean, when you have those.
Yeah, you have a bunch of operations which come from on the periodic cyclic complex or whatever. For example, on the periodic cyclic complex coming from the action of the opera, then you have a Gauss-Manin connection, so which then in homotopy sense, whatever, or if you go to homology, just literally moves this periodic cyclic complex with homology along the moduli space. And if the chain is right, and it's paper, it's recent paper in the archive, like 70 something pages. These operations are preserved. And actually it's true even since the operand lives over integers, so it's true even in finite characteristic in some sense. Yeah, so, but this is kind of for whatever standard Gauss-Manin connection, Getzler Gauss-Manin, I would say, Getzler. And so, but you have some extra structure which is associated with a choice of different, this lambda 0, lambda 1, whatever, and probably higher stuff. So what's happened, how to combine those operations with this extra structure, what's happened? Have some other operators acting on the periodic complex.
Yeah, let me think. So first of all, I mean, well, what we have those, and so you do get n-ary, you know,
Yeah, something like that.
so we do have those operations, and I think there is, those are, you know, disks and cylinders. I think there is no doubt that it's at this level, but I have to think, I guess, I don't know. So this is one thing. And what you are asking, I have to think, but somehow I would think, you know, that if you have this kind of machine of non-commutative calculus, somehow you should be able to get such a result from there, but I don't know.
Okay, and another question, what kind of physics did you mean? You said that it resembles some physics. What physics one should look at if
I mean,
one wants to look at something in physics?
I mean,
yeah, you said that it resembles some physics.
I mean, I have no idea. I have some, you know, something like Fock space.
In this sense.
Yeah.
Yeah. It's interesting. Yeah, this is interesting.
something.
it doesn't have any kind of, so you have some Fock space modeled over the formal series and whatever, two infinity variables. This, yeah. All right. Okay, so it's a bit formal to understand. No vertex vertex separators, something like that. Okay.
Yeah, so something involving something. Something like this, and actually something like this. Those are those A's, B, C's are quadratic in momenta. I mean, I don't know. It's really, to me, it's very much suggestive of something, but I have no idea.
By the way, what you've been talking about, is it published somewhere?
It's actually, I think it's already published, or at least accepted in Ezra's volume.
Yeah, but Ezra's volume is available for elite, and archive is more democratic. Is it something in the archive?
Not yet. I had some.
Ah.
Yeah, it is on my webpage.
Okay, good.
Yeah, I should be putting it on the archive.
Yeah, okay. But if it's on your page, so it's available.
It's on my page like an article, and also like part of our book with Richard Nest, if you want a bigger context.
Yeah, but it's a book. You've been writing it even maybe longer than we write with Maxim some of our papers.
Yeah, right. No, but it is there, and it's on the webpage. Yeah.
Okay. All right. Okay. All right.
I mean, not finished.
Okay. Yeah. Good. No, good. Interesting. Quite interesting. All right. Well, then, yeah. Thank you very much.
Thank you. Yeah.
A really intriguing thing.
Yes.
And so those who are interested, you can visit Boris' homepage and read more. All right.
Put in the archive soon. Yeah.
Yeah. All right. Thank you. And this is it for today.
Oops.